So 3.2a is exponential decay. Okay, and then we're going to connect negative exponents. So what is exponential decay? This is a pattern of decay in which each term is multiplied by a constant fraction. Okay, and then, so this fraction has to be between 0 and 1. So again, I use fraction as a very loose term because the fraction can't be like 5/2 because that's greater than 1. It has to be a decimal, so 0 decimal something. Okay, so fraction between 0 and 1 to produce the next term. So how this graph changes is now that it's decreasing at a constantly decreasing rate. Okay, the equation is still going to be the same where A is the initial amount, B is the base factor. This time our base factor again is going to be between 0 and 1. It's not going to be 0 because then the entire equation would equal 0 every time. And it's not going to be 1 because then we would get a horizontal line. 1 is not a decay or a growth. N is still the number of compounding periods. So this time we're going to get a graph that looks like this. Okay, we read graphs from the left to the right. So as you can see, this is actually going down and to the right. Okay, it also approaches this horizontal asymptote. So naturally we have a horizontal asymptote at y equals 0. Okay, so example 1, uranium is commonly used as fuel for nuclear reactors. This is like an actual thing. Uranium has several different forms of isotopes, some of which occur naturally and some of which are produced through nuclear fission. So one isotope of uranium is U-239. You're going to encounter a lot of these questions in mathematics. This 239 is a title. It has nothing to do with any calculation. Okay, so no calculation. It's just a title. Okay, it decays. That means it goes down, right? Decay looks like this. Or changes into a new substance called plutonium-239. Again, this doesn't matter. You can actually scratch it out so that it doesn't confuse you. Okay, this highly toxic waste material has a half-life of 24 years. So we have something called a half-life, and that is when our base is 1/2. This happens every 24 years. So this time, the T is not 1 year. The T is going to be every 24 years. So what we're going to do first is we're going to model the decay of 50 milligrams of this substance using the following table. Okay, so let's start there. So the original amount is 50 milligrams. Okay, so here's the thing. Rn is going to actually be, oh, I see that back. Rn is going to be the half-life periods. So if n is 0 half-lives, sorry, our T is 0. So our amount is 50. That's our starting amount. Okay, so A at n, this is the amount after n number of compounding periods. Okay, one half-life is actually going to be 24 years. So the amount after one compounding period, so remember n, one compounding period is half of 50. Okay, so two half-life periods is actually going to be 48. So half-life of that, half of 25 is 12.5. Okay, 3 half-life periods is going to be 72. So after 72 years, there's going to be 3 half-lives, and we're going to be down to 6.25. Okay, and then the last one is 72 plus 24, 96 years. So after 96 years, 4 half-lives have occurred. We're going to be down to 3.125 milligrams of this substance. Okay, our equation is going to be the amount at time n equals our initial amount times 1/2 to the n. N in this case, remember, is not years. You have to actually convert it into years, which I'll show you, but this is the number of compounding periods. Okay, so we know first and second differences are not going to work, so let's just show that. Okay, 3.125 minus 6.25 equals, it's negative 3.125. 6.25 minus 12.5 equals negative 6.25. 12.5 minus 25 is going to be negative 12.5, and then 25 minus 50 is going to be negative 25. Okay, so obviously first difference is this is not linear. Now, negative 3.125 minus negative 6.25, so kind of plus, I'm going to get 3.125. You guys see a pattern, how like it's kind of a half here? Okay, negative 6.25 minus negative 12.5, 6.25. Negative 12.5 minus negative 25, okay, so plus, this is going to be 12.5. So again, second difference doesn't work. It's not linear, it's not quadratic. Let's try the ratios. So if we put 3.125, so remember the ratios were going up the y column still. We're actually going to get a half. How convenient. Actually, let's do this in purple. Okay, so back to the y column, 625 over 12.5. Okay, we're going to get a half. 12.5 over 25, we're going to get a half. 25 over 50, we're going to get a half. How convenient. The ratios are consistent, so it's exponential. And how convenient is it that the ratios are 1/2, just like our base? So D, sketch the relation, and then is there a relation a function? Explain why or why not. So what we're sketching here, if we take a look at the values on the x-axis, we're actually going to sketch time. So this is going to be the t-axis. This is going to be time. Okay, and then this is going to be the amount. Okay, you can also graph it against n, which would just be like 1, 2, 3, 4, 5, the number of compounding periods. Okay, but at time 0, we started at 50, we went to 25. Half of that is 12.5, half of that is just over 6, and then 3. Okay, and this exponential graph is going to approach a equals 0. Okay, this horizontal asymptote. And yes, this is a function. And the reason is because, well, we can say it passes the vertical line test. But we can also say each x, which is like t value, corresponds to at most one a value. Okay, and E, assuming that this trend continues, use your equation to calculate how long it'll take for the sample to decay to 40% of the original amount. Okay, so if we still wanted to use the n, so starting at 50 half-lives and then n being the number of compounding periods, let's think about what 40% of the original is. So what's 40% of 50? Well, I get 20. So what we would do is we would sub in 20 for the amount and we would solve. And take a look at this. When we divide out the 50, so 20 divided by 50, we actually get 0.4, which is 40%. Okay? At this point, we need to determine 1/2 to what number equals 0.4. So if we do 1/2 squared, we get 0.25, right? Well, what about 1/2, because we're getting smaller. What about 1/2 to the 1? Well, we get 0.5. So we know that our number is going to be between 1 and 2. Okay, what about 1/2 to the 1.5? Okay, put that in your calculator. I get 0.35. Okay, and if you keep putting numbers into your calculator, you'll get 1/2 to the 1.3, and that's going to equal 0.4. Okay, so if you think about it, 1/2 to the 0.4 is going to equal 1/2 to the n. So n equals 0.4. This is the number of compounding periods. So the number of half-lives that we have to go through is not even a full half-life, it's just 0.4. So how you can convert that to years is multiply by the number of years that this half-life is. So 0.4 times, oh, sorry, it's 1.3. Sorry, it's 1.3. Okay, so if we multiply 1.3 by 24, we get 31.2. Okay, so therefore it takes 31.2 years to decay to 40%, okay, of the original amount. Okay, example 2, a hospital uses cobalt-60 in its radiotherapy treatment for cancer patients. Okay, just to let you know, cobalt-60, this is the name. So I'm just going to scratch out 60 because we don't want to confuse this with any part of our calculation. Okay, cobalt-60, again, scratch out, has a half-life of 5.2 years. Okay, so really awkward this time, 5.2. But all this means is that every 5.2 years, half, or like 50% of the original amount, has decayed. Okay, so it's decreasing 50%, 50%, 50% every 5.2 years. Okay, the hospital has 80 grams of cobalt-60. Okay, so 80 is going to be our A, and like this half-life, that's going to be our B. It requires at least, here's a stipulation, okay, it requires 64 grams to actually provide an effective amount of radiation. So what we're going to do is we're going to write an equation that models the half-life of cobalt-60. Okay, so the amount after n number of half-lives is going to equal our starting amount, which is 80, times a half to the n. Okay, and after we do the question in the number 1, Roman numeral number 1, I, and then we'll apply like the 5.2 years. Okay, and just to let you know, A is going to represent the amount of cobalt, and then N is going to represent the number of half-lives. Lives, that's with a V. There we go. Okay, how often, use your equation to determine how often the staff must replace the cobalt in their machine. So we have the amount after n compounding periods is 80 times a half to the n. Okay, we know that we must have 64 left in the machine. So we can sub in 64 and then just divide out the 80. Okay, and we're left with 0.8 equals 1/2 to the n. So what we have to do is we have to figure out 1/2 to what number equals 0.8. So literally just take your calculator and go 1/2 to the 1 is 0.5. Okay, but if we do 1/2 squared, we're going to get 0.25. So we're actually going away from what we want. Okay, so let's go 1/2 to the 1/2, like 1/2 to the 0.5. We get 0.7. Okay. What about 1/2 to the 0.4? we're going to get 0.75. Okay, we're almost there. 1/2 to the 0.3. Okay, let's go 1/2 to the 0.3. I'm going to scroll down. So I see that 1/2 to the 0.3 is actually 0.8. Okay, so that's pretty close. So I know that n equals 0.3. So it doesn't even take 5.2 years to actually decay. It just takes a fraction of that compounding period. So to see what the number of years is, all I would do is multiply that by the number of years each compounding period is. 1.56. So therefore, it takes 1.56 years, and then they have to top it up. Okay, number 2, we're going to use our equation to determine the amount of the original sample after 1 year. So if we think about 1 year versus the 5.2 years of a compounding period, what percentage or what fraction of a compounding period is that? Okay, so we can actually sub this in, or it's about this percent, so like 19.23% of a full compounding period. So the amount at, and I'm going to actually use this ugly fraction because it's going to lead us into new equations. Okay, the amount at 1 year out of 5.2 years of the compounding period, and then this would have to be, like if you're going to put this fraction into your calculator, it has to be grouped. Okay, so we're going to get 80 times, and then try this in your calculator just so that you know that you can calculate it. 80 times 0.8752. So we're going to get approximately 70. So therefore, 70, is it milligrams? Grams is left after 1 year. Okay, and number 3, how long will it take for the sample to decay to 20% of the original amount? So when I think of the original amount, 80, I'm like, okay, well, what's 20% of that? I get 16. So we're going to sub in 16 equals 80, 1/2 to the n. So here's the thing. When we divide out by 80, again, 16 divided by 80, look at this, 20%, 1/2 to the n. Okay, again, we have to figure out when does 1/2 to the n equals 0.2. So I know that 1/2 squared is 0.25. So I'm kind of almost there. So 1/2 to the exponent 2. I'm doing 2.1, 2.2, 2.3. Okay, so 1/2 to the 2.3 is going to equal 0.20, okay, and so on. So I'm good with this number. So it's going to take 2.3, this is n, compounding periods, but a compounding period is 2.5 years, or a half-life period is 2.5 years. So this is going to take 11.96 years. Okay, so therefore it takes 11.96 years to decay to 20% of the original amount.